Welcome to Key Knife's technical presentation on chipper theory and the development of our KPS chipper system. The KPS development project took place at our 50,000 square foot manufacturing facility in Tualatin, Oregon. It began with a close examination of every chipper knife system on the market, including our previous systems. After reviewing the available options for high production pulp mills, chip mills, and in-woods chippers, we knew there was not a system available that could truly be customized to each operation while having the durability to withstand the most aggressive applications. The KPS was developed for two reasons: customization and durability. We knew that in order to provide the value that Key Knife is known for, we needed to develop a robust and bulletproof system. Our development process was divided into three phases: computer simulation analysis, lab testing with static load and dynamic load testing, and finally, performance verification, where we proved the system's capabilities in different mills across North America. The first phase of the development process began with computer simulation analysis, or finite element analysis. With the KPS, we knew we must design the system with the highest level of durability so it would perform flawlessly in the most challenging applications. Finite element analysis is a computer simulation where the computer attaches a mesh grid over the system components. The mesh grid allows us to see the high and low stress points throughout the system when we apply an operating model. The operating model we simulated was a 12-foot log, 24 inches in diameter, dropping 18 feet directly onto the bevel of the knife, moving at 6,000 feet per minute. The analysis combines this environment with the known strength of the materials used in the KPS. Immediately, the advanced design of the KPS proved its superior strength. By placing the clamp flat on the holder, we eliminated high stress points in the bolts. Based on our FEA testing, under these extreme conditions, no part of the KPS exceeded 60% of its tensile strength, eliminating fatigue as a durability issue. This analysis proved the KPS is 30% stronger than any other indexable knife system available. The second phase in our development process is verifying our FEA analysis with impact testing. We performed dynamic impact tests as well as static load tests. Our first step was to attach stress gauges to the most vulnerable areas of the system based on our computer simulation. The stress gauge sends an electrical signal to our monitor upon compression or extension of the wire. In order to truly compare the KPS with other indexable knife systems, we also performed the same tests on all other systems. The result was consistent with the simulation. The KPS proved to be the most durable. For the first impact test, we dropped a 12-foot, 20-inch diameter log from 18 feet onto the tip of the knife. The system was attached to a fixture to simulate being bolted onto a chipper. With the KPS, there was no damage to the knives or bolts, and the effect on the strain gauges proved our FEA testing was correct. The KPS is 30% stronger than any other indexable knife system. We also dropped 2,000 pounds of steel from 3 feet directly onto the tip of the knife. We repeated this high-impact test until all of the knives fragmented. The results from other indexable knife systems showed clamp, bolt, counterknife, and knife breakage, whereas the KPS showed only damage to the knives. The development process concluded with the KPS being installed at various mills around North America. The results showed the development and testing that Key Knife put into the KPS really paid off. Mills experienced the following: increased production time due to a faster knife change and extended knife life, improved chip quality, no downtime due to system failure, and minimal impact from metal contaminants passing through the chipper. In conjunction with development of the KPS, we began the most extensive research project ever conducted on chip formulation theory. We realized that to truly grasp the customization ability of the KPS, we needed to expand our already vast knowledge of whole log chipping. The project began with a geometric math model where we analyzed the forces involved in chip production and what variables the KPS can control. As you can see here, there are numerous angles and settings involved in chip formulation. The four key variables that we can control are extension, gap, attack angle, and relief. Using a math model, we were able to predict chip formulation, power consumption, and component wear. We took the known strengths of the KPS materials and the known strengths of the specific wood species involved. For example, by studying the attack angle, we have a clear understanding of what setting will provide the right mix of log stability and pull-in force. After building the math model, we designed a chip simulator to replicate the whole log chipping environment. We placed strain gauges on different stress points on the system to show where the forces are being applied. The gauge showed the effects of different knife settings on power and chip formulation. This simulator allowed us to examine different settings and their effects on chip formulation and power. We performed these tests on a wide variety of wood species: aspen, maple, oak, and southern yellow pine. This knowledge allowed us to optimize the settings based on each mill's operating environment and desired chip distribution. The KPS is the only knife system that can customize each variable independently of each other, giving a mill greater flexibility to adapt to their environment. Let's take a look at a recent KPS installation. The KPS was installed in November 2003 at a chip mill in South Carolina. The mill is owned by one of the world's largest paper producers, and they have 5 chip mills in South Carolina. The mill uses a 96-inch 8-knife full-jim chipper to chip tree-length pine and hardwood. The mill was chosen because of its exceptional chip quality and efficient operation. The primary objective was to cut knife costs and maintain quality while eliminating the dangers associated with conventional knife systems. The KPS not only met the challenge, but improved chip quality and overall operating efficiencies. By applying our knowledge of chipper theory and customizing the KPS for their specific environment, Key Knife tightened their chip distribution by 1.5%, 0.7% off of the pins, and 0.8% off of the overs. In addition to this added value, the KPS also reduced operating costs. The operators prefer the KPS over conventional knife systems due to the ease of use and safety, while the mill managers are satisfied with the improved chip distribution and lower costs. The customization ability of the KPS combined with our knowledge of whole log chipping made Key Knife the only solution for progressive mills looking to improve chip quality, production, safety, and overall operating efficiency. Key Knife would like to thank you for taking the time to watch the technical presentation on the KPS chipper system.